Good day everyone! We are the Group 5 of Bio 20-C5
under Professor Christian Tan,
and our topic is all about
intelligent materials.
Smart materials are designed materials that have one or more properties.
Normal materials have limited responses.
Smart materials have appropriate responses.
But response is the same every time.
Here are some examples of the intelligent materials that we will show you.
Velcro. The hook and loop fastener was conceived in 1941 by Swiss engineer Georges de Mestral, who lived in Comogny, Switzerland.
In 1941, Swiss engineer Georges de Mestral decided to take his dog for a nature hike. The man and his faithful companion both returned home covered with burrs that kept sticking to his clothes and his dog's fur. With a burning curiosity, he ran to his microscope and inspected one of the many burrs stuck to his pants. He noted the 100 of hooks that caught on anything with a loop, such as clothing, animal fur, or even hair. With this, he saw the possibility of binding two materials reversibly in a simple fashion, if he could figure out how to duplicate the hooks and the loops. Mechanizing the process of weaving the hooks took 8 years, and it took another year to create the loom that trimmed the loops after weaving them. In all, it took 10 years to create a mechanized process that worked. He submitted his idea for patent in Switzerland in 1951, and the patent was granted in 1955. Velcro got its first break when it was used in the aerospace industry to help astronauts maneuver in and out of their bulky spacesuits.
In 2003, Andre Jem and fellow researcher at the University of Manchester succeeded in creating a synthetic material and mimic gecko feet called gecko tape.
In fact, some of nature's most ingenious tricks depend on surface structures built on a really tiny scale, far smaller than a human hair. The iridescent color of this butterfly comes from the way light scatters across the textured surface of its wing, not because of any pigment. This lotus leaf is self-cleaning, thanks to tiny needle-like protrusions that repel water. The droplets roll off the leaf, taking the dirt with them. And this desert beetle has tiny bumps on its back that collect moisture from the air until just the right breeze blows the droplets down to its mouth. In each case, nature has come up with something new just by manipulating the surface of a material on a very small scale. Now, scientists are trying to do the same thing, to create new powers, maybe even superpowers. Like Spider-Man. Now, in case you aren't that familiar with Spidey, he depends on tiny structures, little hooks on the tips of his fingers that let him climb walls. Can we create a material, a smart adhesive, that will let us do the same? Turns out the best bet for that doesn't come from a spider, but from another natural wonder, the gecko.
While composed of different materials, the gecko tape has a similar structure to the toe pad of the lizards. The fabrication process of the tape involves many cutting-edge nanotechnology methods. First, a polyimide film substrate is prepared on a silicon wafer. Then, an aluminum mask is created through electron beam lithography, a process where a beam of electrons is used to create nanoscale patterns on a surface. This mask is then transferred to the polyimide film through dry etching, a procedure where ions are bombarded against the metal to remove the mask, leaving only the substrate and the projecting polyimide hairs. The material is then removed from the silicon wafer and attached to a flexible base, which allows the materials to adhere better to surface, which is usually not flat due to microscopic imperfections in order to test the adhesive force of the resulting array of polyimide hairs. Game used an atomic force microscope with a cantilever tip and measured the deflection of the tip. As hypothesized, each hair had around the same adhesive force as a single gecko seta. In the future of biomimetic adhesives, while many problems still obstruct immediate commercial applications of gecko tape, such as poor durability and high fabrication costs, the prospects of technology are still generating excitement in variety of fields. An adhesive material that exploits intermolecular forces could be crucial in certain environments where conventional adhesion tools such as suction and glues cannot function. For instance, a descendant of gecko tape might enable astronauts to perform spacewalks with the tape affixing the astronauts' boots to the spacecraft, eliminating the need for complex hardness. In more typical circumstances, the incredible strength of gecko tape could be used in a myriad of applications, such as increased mobility for humans in construction, inspection, and military situations. The fact remains that as we progress in our understanding and utilization of the most fundamental forces of nature, we will be able to approach problems once through unsolved from a new direction, specifically from the bottom up.
Our motivation is that we want robots to go anywhere. So we've had robots that can run along the ground for some time. The unmet challenge was to get robots that could go on vertical surfaces, especially smooth ones.
Imagine a world where robots could climb anywhere. Everything from everyday tasks like window washing to specialized ones like emergency rescue or surveillance would change. The key gecko feature on this robot is the material used for the pads on its feet. They're made from silicone rubber. Tiny wedges on the upper surface of the pad use the same gecko principle of directional adhesion, adhering when dragged down because of the close contact, but the rest of the time not sticky.
This is one pad on a little suspension with a weight about 200 grams below. If you just touch it to the surface, it's not sticky at all, but if you let the weight hold it,
oh man,
sticks perfectly.
So
and now
the weight is pulling down. That's the directional thing you're talking
exactly. And then to get it off, you actually have to remove the weight, and then it will lift right off.
about. So it's quite firm now, but if I lift up, oh my gosh, it's like electricity was turned off.
That's directional.
And that's what the real gecko does.
And that's what the gecko does. And in fact, if you've ever seen a gecko going head first down a wall, you'll see that it's turned its rear feet backwards. And it has to, otherwise it wouldn't stick.
Time to see the gecko in action. The lab's most recent creation, StickyBot 3.
This is a ground granite slab, like a kitchen countertop. So
Okay.
it's too smooth to use something like little hooks or spines. So we really have to rely on the adhesion.
Start the gecko! Pretty impressive. And especially when they show me a piece that supports 45 pounds. I start having my own ideas. If I had gloves made of this stuff, plus socks, could I not make myself a gecko costume that would let me climb walls?
You're not designed to be a gecko. You'll get tired, but you should stick.
They say gecko adhesives would be useful anywhere you need extra grippiness. You know, tires or surgical bandages or sports equipment. But come on, we all know the real reason to develop gecko adhesives. So you can do this! Okay, I'm busted. Nobody has gecko gloves this good. At least, nobody who's talking. Military. But they're coming, mark my words. Until then, Hollywood's Spider-Man has got the job.
Lotus effect, self-cleaning surfaces. The lotus effect refers to the very high water repellence, super hydrophobicity, exhibited by the leaves of the lotus flower, Nelembo.
Dirt particles are picked up by water droplets due to a complex micro and nanoscopic architecture of the surface, which minimizes adhesion. Technological application. Some nanotechnologies have developed treatments, coatings, paints, roof tiles, fabrics, and other surfaces that can stay dry and clean themselves in the same way as the lotus leaf. These can usually be achieved using special fluorochemical or silicone treatments on structured surfaces or with compositions containing microscale particulates. Superhydrophobic coatings comprising Teflon microparticles have been used on medical diagnostics slides for over 30 years. It is possible to achieve such as effects by using combinations of polyethylene glycol with glucose and sucrose or any insoluble particulate in conjunction with a hydrophobic substance. A self-cleaning of superhydrophobic microscopic and nanoscopic surfaces is based on a purely psychochemical effect. It can be transferred onto technical surfaces on a biomimetic basis. One example of the product with superhydrophobic self-cleaning properties is the facade paint Lotusan.